Okay, everyone, today we're looking at what's called the trapezoidal rule. Now, the trapezoidal rule is another way of finding the area under a curve using, we call them trapeziums, but they're also called trapezoids. So another word for trapezium or trapezia are trapezoids, okay? Do not write anything down. You're just going to watch this video, okay? So I just found this on the internet last night. I'm still going to do my own notes and everything, but this will give you a quick overview, probably quicker than what I can do it, okay? We're just going to watch. Okay, and I'll pause the video throughout just to explain some things because they do use slightly different notation to what we use, okay? Oh, we need sound. Covering up my... Okay, here comes the video. Is it starting?
Welcome to a video on the trapezoid rule of numerical integration. When trying to evaluate definite integrals analytically, sometimes it's very difficult or even impossible to determine a function's antiderivative.
Antiderivative is antidifferentiation or the integral. Okay, so the antiderivative is the integral. You don't need to.
So when the analytic method fails, we use a numerical approach to approximate a definite integral.
What that means is there are some functions that you can't integrate. Okay, there will be some types of functions that you cannot integrate. You know, at the moment we just know how to integrate x to the power of n and ax plus b to the power of n. But until we get to do logs and exponential functions and all that, you cannot integrate some certain functions. So we can actually use this rule called the trapezoidal rule to integrate or find the area under the curve of certain functions that we can't integrate. Okay?
And the trapezoid rule is a numerical method to approximate a definite integral using trapezoids. Let's take a look at how this is going to work.
Now, it is an approximation method. This does not ever give you the exact area under the curve. So the trapezoidal rule and what we're going to be doing tomorrow, the Simpson's rule, they are just approximation methods to finding the area under a curve, okay? Now, just watch.
Let's say we want to use a trapezoid to approximate the definite integral of this function on the interval from 0 to 8, the area bounded by the function in the x-axis, represented by the definite integral. However, watch what happens as we increase the number of trapezoids.
Now, sorry, I stopped that video while it was going through, but you know, if we're trying to find the area under the curve here, it's this darker green under here. But if you form a trapezium from the end point to from the beginning to the end, you end up with that trapezium. I'm just outlining it there. Can you see that it's going to be way bigger than the area under the curve? Okay? What's happened to my sound?
You can quickly see that as we increase the number of trapezoids,
can you see how it's become?
The area of those trapezoids is going to approach the value of that definite integral.
Oh, I don't want to do that. See what's happening?
Let's go and take a look at another function. Again, watch as the number of trapezoids increases.
So that triangle is obviously too small. And now as we get more trapezoids... You
can see it quickly approaches the value of that definite integral on the given interval.
Do you get the idea of this? We're doing trapezia.
Okay, let's go back to our presentation. Let's do a little review first. Remember, a trapezoid is a quadrilateral with one pair of parallel sides.
Do you not get this, what that was all about? You don't? All right, so let's just go back.
So determine the
How do I go back, guys? Yeah, but everything's in my way. All right, we'll go do it again.
Use a trapezoid to approximate the definite integral of this function on the interval from 0 to 8. You can.
So, if you're asked to find the area under this curve, it's that dark green bit. Another way of doing it is to form a trapezium from, see how your curve, your first x value of the curve is here and the last x value is there. If I just draw the sides up to where the function is and then form a trapezium, I can find the area of the trapezium. But obviously that trapezium is way bigger than the area under the curve. As we form more trapezia, you're going to end up with a closer value. The area of all your trapezia is going to get closer to the area under the curve. Can you see a trapezium shape there?
Yeah.
All right, now just watch as he forms more.
See, if we use one trapezoid in green, this area is much larger than the area bounded by the function in the x-axis, represented by the definite integral. However, watch what happens as we increase the number of trapezoids.
All right, that's 3 trapezia. 1, right, we've got 2 trapezia. Well, those 2 aren't trapezia, they're triangles because they're touching the bottom, because one side length of the trapezium is 0. So sometimes the trapezia won't be trapezia, they'll be triangles. But can you see that if we do the area of that trapezium and these 2 triangles, it's closer to the area under the curve, right? Okay, we've now got 1, 2, 3, 4, 5, 6, 7 trapezia. Some happen to be triangles when you hit 0, when one of the sides is length 0. But isn't that getting closer to the area under the curve? So trapezoidal rule is just finding the area of each trapezium. And how would you find that? By finding this length. Just watch. This length. Isn't the area of a trapezium h on 2, a plus b? So isn't it, just watching the board because I've got my cursor there, it's that length there plus this length times this height divided by 2. H on 2, a plus b. Then you do this trapezium. H, that length on 2, a plus b. All right? So we'll just keep going.
You can quickly see that as we increase the number of trapezoids, the sum of the area of those trapezoids is going to approach the value of that definite integral.
Now, obviously, 1 trapezium there was ridiculous because
Let's go and take a look at another function. Again, watch as the number of trapezoids increases.
So the actual integral, when it's worked out, is 15. Area is 15 units squared, but the estimated area with one triangle is only 11.3. Can you see, because that green triangle is smaller than the area under the curve, is the green and the purple bit, but one trapezium, obviously, in this case, if you just use one trapezium, half the time you're just going to get a triangle because the bottom length is 0. As you increase, see, we've now got, the integral is 15, but now we've got 14.8,
the value of that
14.9
on the given interval.
Okay, 15, it's almost identical.
Let's go back to our presentation. Let's do a little review first. Remember, a trapezoid is a quadrilateral with one pair of parallel sides.
Now, when we do trapezium formula, we do a plus b. They're just calling it b1 and b2, okay? That's the only difference. So we do h on 2, a plus b. They're doing a half a plus b times h, same thing, but they're calling it b1 and b2. They call them bases. They call it base 1 and base 2, all right?
So to determine the area of a trapezoid, we have the area equals 1/2 times the quantity of base 1 plus base 2 times the height, and this would be the diagram. However, we're going to be using right trapezoids, which means we have 2 right angles
we're doing these
in the
types.
trapezoid. The trapezoid will also be rotated from what we're used to seeing. So this will be base 1 and base 2.
Which is our A and B.
And the height would be the length of this side here.
Okay, now.
Let's say we wanted to approximate this definite integral in yellow by using 4 trapezoids on the interval from A to B.
Okay, now, with this question here, if we want to find the area under the curve here, we've decided that we're going to use 4 trapezoids. In the questions you'll be doing later, it's called 4 subintervals, okay? If there's 4 subintervals, like 4 spaces, 4 trapezoids, so 1, 2, 3, 4. If there are 4 spaces or 4 subintervals or 4 trapezoids, notice how many values of x do we have to look at? x0, 1, 2, 3, 4, 5, okay? So you'll always have one extra value for the number of trapezoids, one extra x value and y value. So remembering that the trapezoidal rule gives you an approximation for the area under the curve. So it's like you're doing an approximation for the integral from b to a of function of x dx, where this is b, we're watching everyone, and this is a, okay?
Well, first, if we have 4 trapezoids, that means n is going to equal 4.
That n is the number of subintervals here, okay? If you look at this and it says b minus a over n, if I want to find, if this is b here, Angela, if this is b here, the point b, and this is a, isn't the width of one of these b minus a divided by 4? So the width of that is whatever b is. Let's say b was 2. Let's say a is 0. All right, what happens if this is 2 and that's 0? That's a length of 2, and then divide it by 4. This would be half a unit length there. So whatever b is minus whatever a is divided by n, the number of trapezoids, or the number of what we call subintervals, that gives you the height of your trapezium. Remember, our trapezia are turned sideways, okay?
So what we would do is we want to divide this interval into 4 equal parts. And one way to do that would be to take the length of the entire interval, or b minus a, and then divide it by n. So when we divide the interval into 4 equal parts, because our n is equal to 4, this would be a, which we'll call x sub 0. This would be x sub 1, x sub 2, x...
Here how he's calling it x1, x2, he's calling it x sub 1, x sub 2, because there's subscripts, not superscripts, all right?
X sub 3, x sub 4, which is also equal to b. We have 4 equal intervals. Next, what we would do is construct our 4 trapezoids.
Come on.
So they would look like this. So our first trapezoid, our second trapezoid, our third trapezoid, and our fourth trapezoid. And we can see this is going to be a pretty good approximation of this definite integral. Let's go ahead and label this trapezoid 1, trapezoid 2, 3, and 4. Remember, the area for the trapezoid is 1/2 times the quantity base 1 plus base 2 times the height.
Which is
We're
a
going to go
plus
ahead and
b.
use it in this form. We'll have the height times base 1 plus base 2 divided by 2. So to approximate this definite integral, we'll determine the area of these 4 trapezoids, where these function values would be the bases of the trapezoids, and the length of each x interval would be the height. And notice they're all equal to each other, and so we can use the formula b minus a divided by n to represent each height of the trapezoid. We have the height times the sum of the 2 bases divided by 2 for the area of trapezoid 1. That'd be f of x sub 0 plus f of x sub 1.
All right. What he's saying here, you need this value here, the length of this. So you would substitute whatever x0 is into the function. Function of x0. And function of x1 gives you this height here, gives you that point there. Remember, each point has an x and a y value. Function of x is the y value. So to find this point up here, it's x1 comma function of x1. Do you get that? How do you get to this point here on the curve? It's the x value, and that's the y value. Function of x1 gives you the y value, or this height here. Function of x0 gives you the height here. Okay?
Divided by 2. So
all right.
This product here would be the height times half of the sum of the bases. So this would be the area of trapezoid 1. Since the height is the same...
Now, are you okay with that? So this is the height. So we're doing function of x0 plus function of x1 divided by 2. That's that's a plus b divided by 2. If you want to work out the area of this trapezium, don't you get this length plus that length, divide it by 2 and times it by h? That's what he's done. That length is function of x0. This length is function of x1. Divide it by 2 and then times it by the height of the trapezium, which is b minus a over n. Now with the second trapezium, it's going to be b minus a over n times function of x1 plus function of x2 divided by 2. A plus b divided by 2 times h. The third trapezium, a plus b divided by 2 times h. The third trapezium will be function of x2 plus function of x3 divided by 2, gives you the average of those two sides, times h, this length here, b minus a over n. And that's what he's doing.
We'll just write the sum of the 2 bases divided by 2 here for the second trapezoid. Well, that would be f of x sub 1 plus f of x sub 2 divided by 2.
So remember,
so this product would be the area
so
of
that's
trapezoid 2.
So remember, that's the height times a plus b divided by 2. Okay? See how we've got the b minus a on n? It's common to all of those areas, so you can take it out as a common factor. The number of subintervals. All right, we'll just keep going.
For trapezoid 3, we have f of x sub 2 plus f of x sub 3 divided by 2. And then for the last trapezoid, we
You're
have
getting
f
the
of
idea?
x sub 3 plus f of x sub 4 divided by 2.
Now, the reason I'm doing this is it's just showing you how we get the rule. The only thing that you're ever going to have to know is the rule. But I'm showing you this video so that you can see how the rule was derived, okay? You don't have to know all this later, all right? But I'm just showing you what the trapezoidal rule is, why it's an approximation, and how the rule is derived, okay?
Again, each of these products, when we distribute,
because you're doing the height times
represents the area of each of these trapezoids. So when we find the sum of those, that'll approximate the area of this definite integral. Now let's go ahead and take a look at one more thing. Notice they all have a denominator of 2, so we could factor this 2 out. So we would have b minus a divided by 2n. And notice that there are 2 f of x sub 1s, 2 f of x sub 2s,
this is
and
the important
2
bit.
f of x sub 3s. So simplifying the numerator, we would have f of x sub 0.
Only one of those.
2 f of x sub 1 plus 2 f of x sub 2s.
Notice there are 2
2 f of x sub 3s. And we have 1 f of x sub 4.
Now, the way
So I want you to notice
the way that I'm going to teach this is with a multiplier pattern. So you'll understand the multiplier pattern. See how you've just got function of x0 here, but we've got 2 lots of function of x1 plus 2 lots of function of x2, 2 lots of function of x3, and 1 lot of function of x4. The multiplier pattern, girls, when I teach this to you, we're just going to drop a little table, and underneath the table, we're just going to write 1, 2, 2, 2, 1, and that's your multiplier pattern. And it makes it really easy to do. I don't get you to learn a complicated formula for this. This is why I'm showing you this. We're just going to learn the multiplier pattern, which is really easy, okay? But once you know how this was derived, that multiplier pattern should stick in your head first, should stick in your head once you see how it's derived. Do you understand how the first... See, this x1 is used in trapezium 1 and 2, and that x2 is used in the area of trapeziums 2 and 3. Do you get it? And this x3 is used to find the area of trapezium 3 and 4. That's why x1, function of x1 is doubled, function of x2 is doubled, and function of x3 is doubled. But function of x4 is only used once, because it's only for the outside trapezium, and function of x0 is only used once as well. Okay?
the pattern of these coefficients. We have 1, 2, 2, 2, 1. So we'll always start with a coefficient of 1, then we'll have 2's, and we'll end with a 1, regardless of what n is. Let's go ahead and formalize the trapezoid rule. Using the trapezoid rule, we can approximate this definite integral.
Okay. When we give you the trapezoidal rule, the one on your formula sheet only uses one subinterval, which means one trapezium. You never ever use one trapezium. So the formula on your formula sheet, you're not going to bother with it because you'll never use it the way it is. So they've put that formula on the formula sheet. It's pretty useless. It's only for one trapezia. No one ever gives you one trapezia. So we're going to learn the multiplier pattern. But the way you learn it is as follows. B minus A, I need everyone to listen. B minus A over N is the width of one interval. You know the B minus A on N? So that's actually H. The way I'm going to give you the formula is like this. Not like that. It's H on 2. Because B minus A on N is H. So the way you're going to learn it, I'll give you notes soon, is H on 2, function of x0 plus 2 times all the middle functions plus function of the last one. And that's how we're going to learn it. Now, when I learn trapezoidal rule, this is how I remember it. Trapezoidal rule's only got 1s and 2s, only. And it will be H on 2, and the multiplier pattern is 1, 2, 2, 2, 2, as many 2s as you need, as long as you've got 1s on the end. Okay? So when we come to do the examples, you'll find that easier. Okay?
Using this formula, and this formula represents the area of a certain number of trapezoids based upon the value of n. And again, I want you to notice that we have 1f of x, 2, 2, 2, and so on, but we end with a 1 as well. So as n approaches infinity, the right hand is going to approach the value of that definite integral.
What he's saying there is that as you get more trapezoids, doesn't the area that you get closer to the actual area? The more trapezoids that you do, did you see that animation at the beginning? So that's what this is saying. As n approaches infinity, this right-hand side here approaches the actual value of the integral from b to a of function of x dx, okay?
Let's go and take a look at an example.
All right. I'm not going to do his example, so I'm going to end that video.
Yeah, no, it's not good class.
Okay, so trapezoidal rule. Remember, it's an approximation method. So the trapezoidal rule uses a trapezium for the approximate, that's really important, for the approximate area under a curve. It, don't write, it generally gives a better approximation than using the above method. Don't write that. See, another way of approximating, I'll just show it to you and don't write. I'll just have a look at this. Another way of approximating is to draw rectangles. Rectangles under the curve. Can you see these rectangles under the curve? Another way to approximate is to draw rectangles under the curve or rectangles above the curve, right? Isn't trapezia better than that?
Yeah.
Okay, so one way that you can approximate is using rectangles above the curve or below the curve. But isn't a trapezium, look, if I draw a rectangle like that and that, watch this. See, that's the lower rectangle, that's the upper rectangle. You know, my trapezium is like that. It's sort of like the average of the upper rectangle and the lower rectangle. The reason I'm showing you this is when you do harder extension things, there will be harder things where they're getting you to find areas with really complicated functions. And they will make you find the area of the top rectangle and the area of the lower rectangle, and then you'll know that the area under the curve is between them. Okay? So that's that concept there, that you've got the rectangle underneath the curve, then the upper rectangles that go above the curve, and your area under the curve lies between those two areas if you ever work them out. But a trapezium is a better idea than doing the lower rectangle and the upper rectangle. Do you see that? It gives you a better approximation because curves tend to be bent. They're not, you know, steps. Okay, so the trapezoidal rule uses a trapezium for the approximate area under a curve. And here we've drawn, here, if you can get that diagram, I might just put it underneath it, you know. Here you've got a diagram of a curve. This is one application of the trapezoidal rule. And we've got, I'm going to do it all under here. You know the area of this trapezium, if that's the y-axis and the x-axis, how would you do the area of that trapezium? I'm going to call this h, that distance there. Isn't the area of a trapezium h on 2, isn't it, yeah, a plus b? We normally see it as that, h on 2a plus b, but using this, isn't it, using this, it will be whatever this is, h on 2 function of a plus function of b, because that's the value of a, that's just what a is, that's what b is, but the length of this is function of a, the length of this is function of b. Now h in this case is just b minus a on 2. Do you get that? H is b minus a. So h on 2 is b minus a on 2, function of a plus function of b. Now that's the formula you get on the formula sheet. Only for one trapezium. Useless. You're never going to be asked one trapezium. So we're going to learn the multiplier pattern, all right? So this is what's on the formula sheet. So area, and I'm going to put approximately your integral. Integral of b to a of function of x dx is approximately equal to h on 2 function of a plus function of b, which is b minus a on 2 function of a plus function of b. You can also see it written as half bracket b minus a, but okay? So this is an approximation. Notice I've got the approximate symbol, this. Approximately. Okay? That's one trapezium. You never do one trapezium. Obviously, the more trapezia, the more accurate. Okay? All right, hurry up. Some notes. Exercise 3.1, trapezoidal rule. To find an approximation of the area under a curve, we can use the trapezoidal rule, which is as follows. Area is approximately equal to h on 2, and then we're going to use the multiplier pattern one, two, 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 etc. 1, which is function of x0 plus 2 times function of x1 plus 2 times function of x2, etc. plus 2 times function of x to the, doesn't matter which one, I'm going to put n minus 1 plus function of x to the n. But you're not going to learn it like that. This is all you're learning. H on 2 and then the multiplier pattern. That's how you're remembering it. So that's the actual rule, but we're not going to learn it like that. We're going to learn it as h on 2, 1, 2, 2, 2, 2, 2, 1. Okay? Now, we're going to do it using a table as well. Okay, remember that h, so where h equals b minus a over n. B would be the end point of your interval. A will be the beginning point of your interval. Doesn't matter what the curve looks like. And n is the number of subintervals. Number of subintervals is the number of trapezia. The number of trapezia. Now, for example, there could be many there. Note the number, this is really important, the number of function values that you will get is always one more than the number of trapezia. So, if they're asking you for 3 subintervals, you will need 4 function values. For example, if you've got 3 subintervals, for example, for 3 subintervals, you will use 4 function values. Okay?
Is they always subintervals?
They'll call them subintervals or trapezia. Because one trapezium is bounded by 2 lines. Do you know what I mean? 2 trapezia are bounded by 3 lines. 3 trapezia are bounded by 4 lines. Does that make sense? And that's why the number of function values is always 1 more than the number of trapezia or subintervals. Okay? For example, for 3 subintervals, you would use 4 function values. Once I do the example, and I better get it done quickly because the bell's going to go, but I only need to do 2 quick examples now. Diagram, that's B, that's A. The width of one of these intervals, or the height of one of the trapezia, will be B minus A, whatever this value is, minus whatever that value is, divided by n, the number of subintervals. Not divided by the number of function values, divided by the number of spaces. You know? Divided by the number of trapezia. Exercise 3.1, question 5. So find the integral from 3 to 1 of x cubed dx using A, 1 subinterval. I'm going to do a quick sketch, and B, 2 subintervals. Now, if you ask for 1 subinterval, you just use the formula on your sheet. Now, y equals x cubed, doesn't that look like this? And they're asking from the value of 1 and 3. And it's an approximation for the area under the curve. You know, if I actually draw that trapezium, it's going to be an overestimation. You know that? because look at my trapezia, it's sitting above. Here's my curve. So what I'm going to do actually with this question, you know, we can actually integrate that one. I'm going to do it with one trapezium. I'm going to do it with two trapezia. And then we're going to see that the more trapezia you use, the closer to the value, to the real value. So if you're asked one interval, isn't that just finding the area of the trapezium? So area is approximately, please use approximation signs. Now you're going to need to know what your function values are. So when function of 1 is, see you need the height here. What's the height? Function of 1 is? This is the curve y equals x cubed. All right, how do you do it?
It's
1. And what's the function of 3? 27. So these are your function values. I'm not using the formula for this, but you could use the formula sheet. Isn't this, how would you find the area of this trapezium? That's 1 and that's 27. So how do you find the area of that trapezium? Isn't it, yeah, that plus that divided by 2 times? Yeah. So on your formula sheet, it's got, where is it? Oh, here's the one. The one on your formula sheet will be this, a half b minus a. This is the one they give you on the formula sheet. Function of a plus function of b, which is approximately equal to a half. What's b minus a? So that's a, that's b. b minus a is 3 minus 1, which is 2, times 2. This is just all they've given you, basically. Right, this is just the formula. You know what they've given you on the formula sheet? The area of a trapezium, basically, which you know, you already knew. So it's a half of 2, isn't it, function of a plus function of b, 1 plus 27, which is 28. A half of 2 is 1, isn't it just 28? All right, so they're saying that using an approximation of one subinterval, pretty useless, that they're saying the area is approximately 28 units squared. Now, let's use 2 subintervals. And then, you know what, I'm going to do 3 subintervals as well, and because we're going to start using what's called the multiplier pattern. Ask more than one subinterval. I want you to draw up a table of values. It's much easier. You go x, function of x. Now, if I've got 2 subintervals, what am I, what's this? If I, yeah, wouldn't I have from 1 to 3 with 2 subintervals from 1 to 3, but I need 2 subintervals or 2 trapezia. What's this value here? So what's the height of each trapezium? 1. So with 2 subintervals, it's b minus a over n. That's what h is. So you learn the formula. H is b minus a on n, which is 3 minus 1 on 2, which is what? 1. So therefore, just leave that for now. I'm going to make this one 4 subintervals so I get nice values. So when x is, so which values of x do I need to do? 1, 2, and 3. So the function of 1 is, what do we get? 1. What about function of 2? 8. The function of 3 is? So here we use the multiplier pattern. I need to get rid of this. I need more room. My multiplier pattern is times 1 times 2 times 1. You know how it's 1 for the end one? 1 for the other end, 2 for the middles. So therefore, area is approximately equal to, the formula is h on 2. What's your h? H on 2 and then your multiplier pattern. Do you know what I mean? So it's h, which is 1 on 2. Whoops. And then I'm going to write multiplier pattern. So what you do is 1 times which ones? So don't you just do 1 plus 27? See how you're doing 1 times that one, 1 times that one, plus 2 times 8. You got that? So it's a half. So this is using 2 subintervals. What's 1 plus 27? 28 plus 16? 38, 44. A half. So girls, they're the end ones. 1 times this one, 1 times that one, plus 2 times the middle value. You'll see as I do more, okay? What's a half of 44? 22 units squared. Now, with one trapezium, we got 28 units squared. With 2 trapezia, we got 22 units squared. I'm going to do the same question with 4 subintervals.
Well,
Wait.
How many subintervals do you never get?
They will tell you how many. So I'm telling you 4 subintervals. The way I want you to do these is do a table of values to get your values. So if you're doing 4 subintervals, how many x values is that? 5. So the first one will be 1. The last one will be 3. H is b minus a over n. Again, same question. Girls, what's your b?
1.
It changes. What's your b? 3 minus 1 over 4 is a half, 0.5. If I decide to do, so that was 2 subintervals. Ones, if I decide to do 4 subintervals, my thing looks like this. So I'm going to do from 1 to 3, but I want 4 spaces. 2 spaces gives me, look, if I want 4 trapezia, each one is going to be half a unit wide. Because 3 minus 1 divided by 4. So the formula is B is your end point of the interval, A is the beginning of the interval, divided by how many subintervals. You have to learn this formula. The height of your trapezium is B minus A over N, which is 3 minus 1 over 4, which is a half. So can we please work out? So we've got 1 for this from before. This is x cubed, remember. Y equals x cubed. What values are we getting? This is 8. That's 27. I need values for 1.5 and 2.5. 1.5 cubed is 3.375. It's best to do it as a, can we do it as just a fraction if you want? Oh, whatever. 2.5 cubed is? That one is 15.625. So what's the multiplier pattern? Times 1 for the ends and 2 for all the middles. So what you do, you draw up your table, you put your x values, you put your function of x values underneath, and you write your multiplier pattern underneath. 1, 2, 2, 2, as many 2's as you need, as long as you've got a 1 on either end. So therefore, the area is approximately equal to, isn't it? You know how I told you that trapezoidal rule uses only 1's and 2's? So it's h on 2, and then you do your multiplier pattern. H on 2 times your multiplier pattern of 1, 2, 2, etc., 1. So it's, what's your h? A half on 2. Now, it'll be 1 times those 2, so it'll be 1 plus 27 plus, now I need to multiply all these by 2. I'm not going to do them individually by 2, but I've got 2 lots of 3.375 plus 8 plus 15.625. Do you get that?
Yeah.
All right, so a half on 2, isn't that a quarter? A half of a half. That's a quarter. 28 plus, I don't know what this adds up to. Is that 15, 18? Is that 19? And 8, 27? Is that 54? Is the answer 72? 82. Yeah. So it's a quarter of 82, which is 20.5. So that is with 4 function values. Not 4 function values. 4 subintervals needs 5 function values because 1 trapezia has 2 values. 2 trapezia needs 3 values. There's always 1 extra value for the number of trapezia. Do you get the idea?
Yeah.
All right, now let's work out the actual integral. The integral of x cubed dx between the values of 3 and 1. This is also going to be a demonstration that the more subintervals you use, the closer. Now, if you look at the 1 subinterval, the actual, it was an overestimation. And I think as you get more subintervals, we'll see anyway. What do you get here if you actually do proper integration methods? What do you do? X4 on 4, substitute in the values of 3 and 1. 4 is what? 3 to the 4. 81 on 4. minus
1 or 4.
minus 80 on 4, which is 20. 20 for the integral. And look which one's the closest. 20.5. If I did 6 subintervals, even closer. 8 subintervals, even closer. Got the idea. So I started off, the actual integral is 20. 1 subinterval got me 28. 2 subintervals got me 22. 4 subintervals got me 20.5. I'm getting closer and closer to the actual answer. The more, yeah. Now I'm just going to do one more question. I'll be very quick. We're just going to have to close the door. Can I close the door? All right, just... All right, yep, as long as they're nice and quiet. Question 8. Evaluate 4, 1, log of x dx using... Actually, I'm going to change it. They're using... Yeah, it doesn't matter. Using 3 subintervals. All right, all you do is, remember yours just substituting values? I want a table of values. X and function of x is log of x, isn't it? Where do you think, what's your b minus a over n? If you're going from 4 to 1 and you're dividing it into 3 bits, what is it? Look at my number line. 4 and 1, I want to divide it into 3 sections. What do you think they're going to be? Don't worry yet. I'll show you. What's b? Don't worry. Girls, isn't it 4? B minus a on n is 4 minus 1 over 3, which is 1. So the first one is 1. The last one's 4. What are the middle two? Go up by 1s. 2 and 3. So my x values are 1, 2, 3, 4. Who's that?
Me.
Oh, okay. All right, now, girls, log of 1. Just put in log of 1 because you're substituting. Log of 2, log of 3, not yet. Log of 4, don't work them out yet. What's the multiplier pattern? Times 1, times 2, times 2, times 1. The area is approximately equal to. What's h on 2? What's h? What's h? It's 1 on 2. Multiplier pattern. Which 2 just get multiplied by 1? Log of 1 plus log of 4 plus 2 lots of what? Log of 2 plus log of 3. So that's what you enter on your calculator. The reason we're using trapezoidal rule here is that you don't know how to integrate logs. That's why this trapezoidal rule, do you know the log button on your calculator? It says LOG, log, not LN, log. So can someone go onto their calculator, just work out, I do the middle bit and then halve it at the end. So do the half, times it by a half at the end, do all this bit, get an answer and then times it by a half. X, function of x, put the multiplier pattern underneath, 1, 2, 2, as many 2's as you need, as long as you've got a 1 on either end. And the formula is, remember, h on 2. And then the multiplier pattern. Okay? All right, girls, your homework is exercise... Oh, no, it won't be too much. Exercise 3.1. Can you do question 6, 7, 10, 11. And girls, in the last 3 questions, there's already a table given to you, but and just do 13 and 14. 6, 7, 10, 11, 13, 14. It's only 6 of those. They're quick.
10, 11, what?
10, 11, 13, 14. So question 6, 7, 10, 11, 13, 14. Use the table, use the multiplier pattern. All right, I'm stopping.